Hello, everyone. Welcome to pre-lecture 10. This is going to be our introduction to equilibrium, which is chapter 13 in our textbook. I know I had said in class that I would do a video example of our last question from the chapter 12 worksheet, which is question number 16, I believe. But yes, question 16, but I'm actually going to save that for class just in case you have questions. I want to make sure you're able to answer those, or I am able to answer those. You are able to ask them in class. So this will be starting chapter 13, but we'll finish up with that in class on Thursday. So for most of chemistry, Gen Chem 1, Gen Chem 2, we've always had our reactants on the left side of a reaction arrow and our products on the right side. And anytime we draw this sort of reaction arrow only pointing one way, we consider that to be an irreversible reaction, meaning that it only goes the one way. However, many chemical reactions are in fact reversible, meaning that they're capable of going both directions in an equilibrium. And so when we have an equilibrium, instead of having our one-way arrow, we have these two arrows shown here. We have example here of N2O4 that splits apart to form 2N2O. And this is a process that is in equilibrium, so it goes back and forth. The relative concentrations then of our reactants and our products will vary greatly. So some systems will have mostly products and maybe only a few reactants when they reach equilibrium. Others may contain mostly reactants, and some are just in the middle. And we're going to talk about how we can distinguish those starting in class, even in this pre-lecture video. However, just a reminder that kinetics that we have been talking about tells us how fast a reaction goes, whereas equilibrium is going to tell us how much of a reaction proceeds towards products versus how much stays in the reactants. And this is a process that is ultimately called dynamic equilibrium. And I will define that a little bit more on this next slide. And dynamic equilibrium is also a way to think about how we connect our kinetics to our equilibrium. And so when a reaction has reached a dynamic equilibrium, that's when the rate, so again, rate is how fast a reaction is going, the rate of our forward reaction and our backward reaction is going to be equal. And so this is kind of shown in these two charts here, where this one on the left is showing our concentration. So once we reach equilibrium at this dotted line, our concentration of products and reactants is going to stay the same. However, that doesn't mean that all of a sudden nothing is happening. It just means that our rates, so we represent these as our rate constant and our concentration of whatever species we have, just means that our rate of our forward reaction and our reverse reaction are going to be equal. And so that's why we have a single line there once equilibrium is reached. Okay. So within that, once that equilibrium has been reached, again, the quantity of products will not change unless we have a change in temperature, pressure, or the addition of more chemicals, which we will talk about next week, how we calculate changes in equilibrium based on those conditions. Okay. So that's with regards to chemical equilibria. In addition to those chemical equilibria, we also hopefully remember from what we've talked about earlier in the semester that some processes exist in a dynamic equilibrium between phases. So if you think about vapor pressure, that is defining a dynamic equilibrium. Another example of that, so shown here on the right, is the element bromine at kind of standard temperature and pressure. It is mostly a liquid, but it does have a relatively high or rather low vapor pressure. So you'll see quite a bit of gaseous bromine also contained within the sampule. Okay. All right, so moving forward with Gen Chem 2, of course, we have our concept and then we want to try and quantify it in some way. And the way we quantify our equilibrium relationships is generally with a reaction quotient, which we give the variable Q, and it's going to be derived directly from the stoichiometry of any reversible reaction. And so our mantra for this unit, and really for the rest of the semester, is products over reactants raised to the coefficients. And so if you notice here, if this is our equilibrium equation, concentration of C raised to the power of lowercase c is representative of our coefficient there. Same is true for D. Our products are on top in our numerator, and our reactants are on the bottom in the denominator. Okay. If we have reactants or products that are gases, we can also express this in terms of concentration, or rather than in terms of concentration, we can express it in terms of pressure. So we have the same thing here, where we have the partial pressure of C, partial pressure of D raised to the powers, still products over reactants, right? And so because of this, any reaction quotient, any Q value is going to end up being unitless. There's another reason for that that's ultimately beyond the scope of this class, but if you take physical chemistry, you will learn all about it, okay? And so this numerical value then, Q, describes the quantities of products and reactants at any point before our equilibrium is reached. And so at that point, we have Q. So again, any point beyond this dotted line is going to be Q. For example, if we start with no product, we'll start to form that product as our reactants decrease until our concentrations remain equal, in which case we've reached equilibrium. And so Q will be extremely high, or I guess Q will be essentially 0 if we start with no products. Q will be close to infinity if we start with no reactants, right? Because that's our products over reactants. So just thinking about kind of the scale that Q can take, right? A big concept, so this is something I will say over and over, but hopefully you get it this first time here, is that once we reach equilibrium, once we have our dynamic equilibrium, we then, instead of defining Q as products over reactants, we define K as products over reactants. So K and Q are just the same exact thing, but one is at equilibrium and one is not at equilibrium. Okay, and so that is how they are defined. And K, again, is going to be a fraction of our products over reactants. The larger our K value then indicates that a reaction will produce more products, whereas a smaller K value will produce fewer products. Okay, hopefully that makes some amount of sense. All right, and so if we have homogeneous equilibria, where if we look at our phases, everything is dissolved in aqueous solution or a gas, then all we have to do is write our products over our reactants raised to their powers. And so we have some examples here. And sorry, this Kp should say Kc. The C stands for concentration, the P for pressure. So that is a small typo on my part, but that is how we would represent our chemical equilibrium going from the chemical equation to our K expressions for these two reactions. Okay, and we can actually interconvert between Kp and Kc using this equation shown here. The key thing is the change in the number of moles of the reactant and product gases. And so we're looking to identify the amount of gases that are involved to convert between Kp and Kc. Okay. Right, we can also have heterogeneous equilibria, and so this is where our products and reactants may be present in different phases. With regards to our other phases of liquids and solids, we do not count these as part of equilibrium expressions. Ultimately, we don't do that for reasons that are beyond the scope of this class, but again, take physical chemistry or quantitative analysis, and we can certainly discuss why that is in those courses. And so equilibrium expressions for something like lead chloride, which is a solid, but then dissolving into Pb2+ and Cl-, this would be its equilibrium expression where we don't include the solid PbCl2. Okay, same will be true for calcium oxide, calcium carbonate. Our K expression is 1 over the concentration of CO2. And we have, of course, some other examples shown right there. Okay, that'll be it for the pre-lecture. Hopefully that made sense. If not, please send me questions or hold on to them and we can discuss in lecture. Otherwise, I hope you have a good day and I will see you in class.